So once again, today we're looking at a cylinder and cross flow. This is a pretty classic fluid dynamics problem that we can learn a lot from. We'll be focusing on the drag force on this cylinder, and in fluid dynamics, drag comes from two different sources. At low Reynolds numbers, viscous forces dominate, but in our experiment, we have a high Reynolds number, so pressure forces dominate. We can determine the drag force from a pressure force dominated flow by integrating the incremental pressure distribution along a whole area of the cylinder. By integrating the pressure of the area, we can calculate a force. For our pressure distribution experiment, it's useful to know the upstream conditions so that we have sort of a reference velocity and pressure to compare them with. We'll measure this using the pedostatic probe. These upstream conditions will also be useful when we're calculating our coefficient of pressure, which is a non-dimensional way to represent the pressure distribution around the cylinder. Much like the coefficient of drag, which is another non-dimensional number, this will allow us to compare our experimental results to those in the literature or from other laboratories. And you can do that using this traverse system, like such. We'll kind of line it up, centered up with the cylinder upstream. With this, we can know our upstream dynamic pressure and static pressure. The pedostatic probe has two different ports. One of them measures the stagnation pressure, and that one is attached to a line that comes out of the top of the stem. So if we follow this line down, we can plug the stagnation port into port A on our pressure transducer. The other line measures the static pressure, and that comes out of the side of the pedostatic probe. And that goes to this line, and we'll plug that into port B. So if we remember that the pressure transducer measures a difference of pressure, if we have stagnation pressure in port A and static pressure in port B, we're measuring the difference between the two. Using Bernoulli's equation, we know that this means that we're measuring the dynamic pressure. By doing this, we can determine the velocity of the flow. So when we have both ports from the pedostatic probe plugged into the pressure transducer, we're measuring dynamic pressure. However, we also need the static pressure alone. So what we'll do is unplug the stagnation line, which is at the top of the pedostatic probe. We'll follow this and unplug it from the pressure transducer. After we unplug that from the pressure transducer, we have in port A the atmospheric pressure, in port B static pressure. So now we have on its own a measurement of static pressure. And so during this, we'll record both the static pressure and the dynamic pressure upstream. Monitoring the upstream dynamic pressure is also important so that we can set our correct wind speed within the test section. If you'll notice here on the control box for the wind tunnel, the readout has units of hertz, which indicates that this is actually a readout of the fan speed in the wind tunnel. So we don't have a one-to-one monitoring of the speed in the test section from here alone. What we'll do is turn on the wind tunnel, hitting the run button, and adjust this frequency until our readout on the pressure transducer matches what our expected dynamic pressure is. The way that we'll calculate what our expected dynamic pressure is by using the dynamic pressure formula, 1/2 rho v squared, and by setting up that equation to use our nominal test section speeds of 15 meters per second and 30 meters per second. Once we calculate that and convert it into units of inches of water, kind of as we calibrated our pressure transducer to read, we can determine what the correct setting is for the wind tunnel. And we'll leave this as an exercise up to you. After we set up the correct wind tunnel speed, we'll need to move our pedostatic probe out of the way so as not to affect the flow around the cylinder. So what I'm going to do is just traverse this up and out of the way so that it's not upstream of the cylinder anymore. It's going to take a while. To be safe, you can just move it as far away as you can. And now we're ready to hook up the pressure tap on the cylinder surface. So we'll follow this line coming from the cylinder and follow it all the way to the pressure transducer. Right now we've still got our pedostatic probe plugged in, so I'll unplug both of those. you should plug this line, which comes from the cylinder, into port B of the pressure transducer. Now it's plugged in, and now what we're reading is the static pressure along the surface of the cylinder. And we can see that there's a scale here that shows us what the angle of the pressure tap is. So as I mentioned earlier, we'll be taking pressure measurements in increments of 10 degrees by rotating the cylinder as such, and marking down the digital readout from the pressure transducer along the way. That way we'll have pressure as a function of angle along the surface, and allow us to integrate the pressure distribution and find the drag force. And we'll do this at both 15 meters per second mainstream flow and 30 meters per second. You should note that at some angles, you may see a lot of fluctuations of pressure. When you start to see this, you should record multiple values so that you can get an accurate mean measurement and quantify your uncertainty coming from those fluctuations better.